so this is a great segue as what is F inverse playing the role of? And it's playing the role of the, let's see, the Lagrangian flow map.
Okay. Yeah.
Right, so this is a perfect segue. So the Lagrangian flow map is the solution to this ODE. It's a random ODE, right? And it's phi t is not a Markov process. It's very important to see. So it's actually UT. So U and phi together are Markov. And so this is the map that tells you where each individual particle goes in the fluid. You see, if you just had the transport, if you just had this transport, no kappa, no external forcing, whatever, then the passive scalar would be the initial scalar composed with phi t inverse. So it's like composition with a Lagrangian flow map from one time to the next time, like over an interval, basically. And so that's what we want to take advantage of. So then that gives us a hint. So what is it about the Lagrangian flow map that we need to prove? We need to prove that it sends low frequencies to high frequencies exponentially fast. That property, as we'll see, is much stronger than just saying it's chaotic. So we first have to prove that this flow map is chaotic. So let's see, let me first state the theorem of what that means. So this was proved in our first paper. And so let me explain carefully what that means, and then I'll start explaining how you actually prove it. So what it says is that there exists a deterministic, it's very important, this number is deterministic, such that you get this kind of asymptotic exponential growth. This asymptotic exponential growth holds almost surely and for all initial conditions. Okay, so there's initial particle, x, and you study the gradient of the flow map with derivative with respect to the initial condition x. So you have x, and then you have phi t of x here. You want to understand the derivative of this position based on small changes of the initial condition. And you want to see that this grows exponentially. This is kind of the most basic notion of chaos. This would be a positive Lyapunov exponent. And so this says that, yeah, asymptotically, this exponential growth rate is exponential. That's what it means for it to be positive, strictly positive. And it's very important to see that this holds as an almost sure property. This isn't some property about how, like, this isn't some like trick about how, like, oh, if you average over the noise, something happens or something. No. So what you really want to see is that every particle in every experiment measures the same exponential sensitivity as time goes to infinity. That's what you really need. So that's what it means to be, for a random system to be chaotic. Okay. So that's what we need to prove, that there is some lambda. We have no idea what it is as a function of nu before you ask. That's an extremely hard problem. Again, we don't understand the hydrodynamics when nu goes to 0. So that's, we don't really know the value of this number right now. As you'll see, the Navier-Stokes case is much harder to prove. That's the hard case to prove this theorem. And for simple models, like if you just kind of impose some this very simple field where you just have 4 shear flows. So you have a shear flow like this and a shear flow like this, and then the natural phase shifts of that. This example satisfies this theorem, and it's much easier to prove that, actually. Yeah. So the thing is, like, so this is an example of what happens when you drop the nonlinearity. A field where the value of each Fourier mode just evolves according to an independent, called Ornstein-Uhlenbeck processes. So sort of solutions to the simplest stochastic ODE imaginable. The thing is that this, if you squint, kind of, you can imagine that the flow map associated with this velocity field will look like kind of like the composition of random shear flows, like shear flow like this, shear flow like this, shear flow like this. It's not, but let's just think heuristically. And the thing is, compositions of shear flows like this and then this are actually hyperbolic. And in fact, the CAT map, which is the canonical uniformly hyperbolic map, is exactly a composition of shear flow like this and then shear flow like this. And so you should totally expect that that this flow should be chaotic, and it should be chaotic unless these z's are correlated in a very specific way. So generally, it doesn't have to be OU processes, just anything that isn't correlated in some pathological way, and we'll make this more precise, this flow will be chaotic. And indeed, like measure preserving systems, like incompressible velocity fields, are going to be normally chaotic. Then it's important to understand that this velocity field, U, is not chaotic. Okay, it's the Lagrangian flow map which is chaotic. This velocity field U is completely the opposite of chaotic. So in the sense that if you take this evolution, this U, and you started with two different initial conditions, the two trajectories will converge to each other exponentially fast. The velocity field. So the velocity field is not at all chaotic in this example, not even remotely. It's the complete opposite of chaos. Okay. It's the flow map, the Lagrangian flow map that it induces, which is chaotic. That is the really important distinction, one of the really important distinctions that we're trying to understand here. This theorem is in no way stating that the velocity field is chaotic. That is as it turns out, a much harder theorem to prove, one that is still open. That problem is still open. Okay, but still, this problem is still hard, as we'll see, and it's not obvious that it should be true. So chaotic dynamics of the Lagrangian flow map, once you turn on the nonlinearity, becomes less obvious, because again, this is what you see, and you see these flows here. When you see this picture, the flow in one of these vortices is going around in an ellipse. This is a not chaotic flow. The gradient of the flow map will grow linearly here, because it's basically like a shear flow. So that the two layers will slide past each other like this. And so if you had a vortex that lived forever, you would not have this chaotic result. So if you had any single vortex that lived forever, or if you had a single particle that was trapped in one vortex and then got traded to another vortex and then got traded to another vortex and then got traded to another vortex forever, this theorem would be false. So the important point is that that cannot happen. So this theorem proves that cannot happen. And that's not obvious just from looking at videos. Yeah, so it should be, I think it's kind of clear that this theorem is much harder in the nonlinear case than in this case. Okay, so let's try to prove this theorem, or give a sort of rough sketch of how one can prove Lagrangian chaos for Navier-Stokes. So the main Markov process that's going to be underlying everything is going to be the motion of the entire velocity field and one single particle. So that's not obvious, but that's what's going to happen. So we want to understand the motion of a single particle, which I'll just call xt. So UT-xt, so again, xt, not a Markov process. UT-xt is the Markov process. And this is called the one-point particle motion, or I'll just call the one-point process. Just want to understand the motion of one particle as it evolves. This is a perfectly well-posed Markov process. The first thing you want to prove actually is that it has a unique stationary measure. And that stationary measure is the stationary measure for Navier-Stokes cross Lebesgue measure on the torus. So I would say proving that's a stationary measure is kind of immediate because of incompressibility, but proving that it's the unique stationary measure is not obvious. And that requires some serious work and some Malevich calculus and stuff. But I'm not going to discuss that. So that's the first thing you want to know, that this Markov process is a unique stationary measure. The next thing you want to understand is that the gradient of the flow map is not the Jacobian of the random dynamical system that we're talking about. So what do I mean by that? So it's not the derivative of zt with respect to the initial condition, because the zt involves the entire fluid velocity field, and that we can't study yet. That's much harder. And also not what we're talking about. And so dx vt is something that's actually more general than the derivative with respect to the initial condition. It's something called a linear cocycle. And don't get lost in this composition. This is basically just the chain rule. So this just says it's a linear operation that kind of follows your Markov process and satisfies this particular type of chain rule, in a sense. This is what is called a cocycle in the random dynamical systems literature. And the first thing you want to check is that this cocycle is kind of not completely pathological. And this just follows from regularity of the velocity field. So by regularity of the velocity field, sort of the probability of this gradient blowing up super ridiculously huge is very small. And so you could get these really minimal estimates, for example. Those minimal estimates are sufficient to apply a really beautiful theorem called the multiplicative ergodic theorem. And again, this is a theory from random dynamical systems, which is sort of like the key field of math which is going to rescue us, is the field of random dynamical systems. So this beautiful theorem says basically it formalizes the notion of an entire Lyapunov spectrum. It's proved by Asladet. I forget how to say this person's name. Basically, so there exists r distinct deterministic numbers, which are the Lyapunov exponents, and you get this crazy flag of subspaces, which is it's harder to write down than it is to understand what they are. So what they are is they are the subspaces on which you see these different exponential growths, basically. So for example, if you're thinking about a 2D system, at every position, every initial condition, there's kind of like a one-dimensional subspace where you'll see the second Lyapunov exponent, and everything off of this subspace, you'll see the top Lyapunov exponent. And what do I mean by that? So like, remember you're looking at the growth of a matrix, right? AT omega Z is this matrix. So it grows or contracts as in different directions. So this says that for all directions outside of the one subspace complemented the other subspace, you see this growth. It's not going to be super important for us. We're really only concerned with the top one for now, roughly. And so basically what this says is that you see this entire spectrum. Anyway, it's a really beautiful theorem. I definitely suggest that you look it up if you've never heard of it. And so you know that there's so the multiplicative ergodic theorem just applies straight up using very simple qualitative estimates. And so you know that you have a top Lyapunov exponent λ1, which is the asymptotic growth rate of the gradient of the flow map, and you know that it's deterministic due to this ergodicity of mu cross Lebesgue. And so the difficult part is proving that it's positive. So proving that there exists a top Lyapunov exponent is not hard, actually. So one knows that actually by incompressibility, the sum of the Lyapunov exponents is 0. And that's really important because that means that in order to prove that λ1 is positive, we just need to prove that it's not 0. And that's a big improvement. So it can either be 0 or it can be positive. It can't be negative. And that's good. And so we want to prove that it's positive, and that's what's called Lagrangian chaos. Like I said, it's not the same thing as saying U is chaotic. Totally different, totally unrelated, a priori unrelated, in the sense that, we come up with plenty of examples that have Lagrangian chaos, but not Eulerian chaos. And it's also easy to come up with examples which do not have Lagrangian chaos, but do have Eulerian chaos. So a priori, they don't go together at all. They're not really connected at all. Of course, in reality, that's not quite true, but the exact connection between the two is completely really not understood at all. All right, so now the key point is we actually have to do this at some point. So there's, it's great to talk about all this qualitative theory. Oh yeah, if the Lyapunov exponent is positive, then blah blah blah. But the hard reality is that it's really hard to prove that a given system has a positive Lyapunov exponent. So in deterministic systems, this is almost impossible. So if I give you a deterministic system, you can't tell me if there's a positive Lyapunov exponent. Even for very simple systems, it's almost impossible. So it's it's completely open for some really simple systems that are almost explicit. And then in the random case, the situation is better, but not amazing. So it's still not that obvious. So there's basically one tool that I know of that will work at least for a general class of random systems. And that, we're lucky, that tool is actually going to work for us if we put a little bit of work in. And this is the key idea to proving positivity here, which is called Alle-Furstenberg theory or Alle-Furstenberg rigidity. Let me explain it first for random matrices. So I'm going to take random matrices, all IID. So I have some measure on SLD, or let's say 2 dimensions on SL2. So this is determinant 1 matrices. And then I'm going to just pull random matrices out of this, sample this measure out of SL2, multiply them together. And I want to ask, when does this grow exponentially fast? So this is kind of our toy model for a co-cycle, because a co-cycle is kind of like that, except instead of pulling them IID, we're sort of pulling them from a Markov process, sort of an underlying Markov process that's evolving, and kind of pulling a different matrix out based on what the underlying Markov process is doing. So the co-cycle case is definitely more complicated. But let's talk about this case first. It's a good toy model for it. And so it's easy to come up with some examples where the Lyapunov exponent is 0. And again, because of determinant 1, the Lyapunov exponent can either be 0 or positive. So the easiest example to see is when you have a random rotation. So A is just kind of a vector. A is just a rotation, for example. So maybe the rotation is random, but it doesn't matter. There's no growth at all, right? The next example, which is maybe the next easiest to come up with, is a shear flow, where A is just kind of shearing vectors back and forth. But assuming that this random alpha isn't, as long as it satisfies the sort of basic properties that it doesn't have a huge tail, this also can only grow kind of linearly or maybe even square root n. Does that make sense to people? You can actually solve this explicitly in this case, and you get A1 is and you get the sum of all the different samples of alpha j. Right? So this could grow like square root n or even n, but it couldn't grow exponentially. Right? Then the last example is when you might have exponential growth, but it keeps canceling itself out. So for example, you can have exponential stretching with probability 0.999, but then every so often, the directions that are getting stretched gets flipped and become the directions that are getting compressed. So you stretch, flip, compress, flip, stretch, flip, compress. And that will also cancel out. So here, this will be like e to the square root of n kind of growth, but that's not exponential, and so your Lyapunov exponent will be 0. And so these are 3 examples that are increasingly difficult to brainstorm. And it's really cool because Furstenberg showed that those are the only examples that you will ever come up with, which is really cool. I think this theorem is really cool. So basically, what does that mean? So what he showed was that if eta was 0, then one of 2 things happened. So either there's some inner product such that you are almost surely an isometry. So that means you have a completely deterministic degeneracy. So there's the inner product is deterministic, completely not random. And the fact that you're an isometry is completely not random. And then the other example is that there's a deterministic number, which is either 1 or 2 in 2 dimensions. And again, deterministic set of lines, such that these lines are just permuted. And so you can see these 3 examples. This is the isometry case. This is the case where you have 1 line, and this is the case where you have 2 lines. And in 2 dimensions, up to changes of variables, that's it. Those are the only counterexamples. every other random measure on SL2 will have a positively operative exponent in this sense. And this is this observation, I think, really cuts to the core of how random dynamics works to some degree. And what it's really saying is that if you have a volume preserving system, then in order to not be chaotic, you need an almost surely invariant structure. So you need some really strong, almost sure invariance. And if you don't have that, then you're going to be chaotic. That's the idea behind this. And so how do we quantify that for our Markov process? So a key tool in random dynamics is what's called a projective process. So this is, you want to understand the stretching or compression in this matrix as it evolves. But you want to do so with a Markov process that somehow lives on a compact manifold. And so what you do is you normalize this. And you can actually show that in this case, it satisfies this random ODE again, at least if you think about it, if you think about it as vector on the sphere. And since we only care about subspaces, VT really, you can think of it as evolving on the sphere, but it's actually, the right way to think about it is as evolving on projective space. So you really, this Markov process, UT XD VT, is tracking the location of a particle and the location of a one-dimensional subspace. That's how you should really think about it. That's why it's called the projective process, because it lives on projective space. Well, VT lives on projective space. This guy lives on UT cross the torus cross projective space. Oh, sorry, this guy lives in our Sobolev space H, torus cross this projective space. So it's really important to understand how matrices act on projective space. And this is key to understanding sort of random dynamics. I think maybe the easiest way to say this, well, okay. Let me just give these two slides and then we can contemplate. So the first one is this interesting formula, which I think really it's a really important formula actually, which says that if you take Lebesgue measure on projective space, so just like the constant measure on projective space, and you push it forward by a matrix, just any matrix, determinant one matrix, then you get a new measure on projective space, and it's absolutely continuous with respect to Lebesgue measure, but its density has to do with the growth, has to do with the size of the matrix. So if the matrix norm is large, you're going to get concentration of the measure. And let's see actually why that's the case with this next example, which, so let's see this example of, let's solve this ODE and see this action of this flow on projective space. So if you solve this ODE, the solution is something like whatever, it's like e to the 2t 0 0 e to, what am I doing? Something like this, right? Oops. Right, so it's going to compress in one direction and grow in the other direction. Something like this, right? No, wait, I think I messed up. This is probably a 1. I was like, that does not look right. I accidentally flipped the, anyway, you see what I did wrong. Okay. So what this is going to do is it's going to, but if you think about what YT would do. So what YT would do is, wherever you start, it's going to compress in this direction and expand in this direction, which means that YT will kind of tilt like this, right? This will be like Y1, this will be like Y2, this will be like Y3. And so if you think on projective space, that will just be where we take these vectors and clamp them back to the sphere. And so they're going to be like this, boom, 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 boom. And they're going to all clamp onto the x-axis. So in projective space, you'd get this subspace, and it would tilt like this onto the x-axis. So the projective process will sort of concentrate. So if you think about starting with a Lebesgue measure and pushing it forward, it's going to flow and concentrate onto the x-axis like this. And so it's really important to see that the stationary measures of the projective process sees the stretching and compression of the flow map. So, and that's the key thing. So the point is that this VT lives on a compact manifold, but it still tells you about the stretching and compression. So one of the steps you want to prove is that there exists a unique stationary measure to this UT XT VT process, and this stationary measure will contain information about the stretching and compression. Okay, so this is the kind of lemma that sort of is like the Furstenberg for where you have a infinite dimensional Markov process driving a finite dimensional matrix evolution. And the version in the paper is totally abstract to that case. But I'm just going to state it here for the Lagrangian, specifically the Lagrangian flow map. So if you can prove that this guy has a unique stationary measure, and you have this strong Feller property, this is the place where we actually really use this assumption about the noise. Everything else in the paper, we don't really need it. But this theorem is where we need it. Then we can prove kind of in this case that we have the following variation of the kind of Furstenberg, kind of like a la Furstenberg dichotomy, where either you have a family now of inner products, so the inner products now vary as a function of the UT-XT process, and such that this guy acts almost surely as an isometry between the two inner products. Okay, so it's much more complicated. Or you have continuously, and it's very important that these inner products and these lines vary continuously. So yeah, you have either a set of inner products or you have a set of lines, which depends on UX, such that the DX, so the gradient of the map, the gradient map deterministically maps these lines to each other. But you see, it's a much more subtle proposition now because you have T's on both sides of this. It's really hard to see what this, what this kind of implies. It takes a lot of thought, at least it took me a lot of thought to understand. And where strong Feller is used is actually to prove that they're continuously varying. So you can actually prove this theorem in some sense without the assumption of strong Feller, but you lose this continuous variation, which if you lose that, I have no idea how to use it to prove anything about Lagrangian chaos. So okay, and so the key thing is that as complicated as these objects are, they are deterministic, and that's the key thing. These guys are deterministic, and these degeneracies are almost sure. Okay. So proving this is hard. I'm not going to give the proof of this lemma. I'm going to say a few things about sort of the finite dimensional versions of the, actually just going to talk just a little bit about even just heuristics about the finite dimensional versions. So let's just think about if my Markov process ZT was on some n-dimensional manifold and I had a general linear cocycle. So it could be the gradient of the evolution, for example, or it could be something else. And suppose that we know there exists a stationary measure for this ZT-VT process. Now, the stationary measure lives, it's a probability measure on kind of the projective bundle of the manifold. And so you can disintegrate it, knowing the fact that you have a unique stationary measure for the ZT process, you can disintegrate it with respect to this measure mu. And so you have these fiber measures, which gives you for every z, you have a measure on projective space, these new z's. And I would say this is a really deep inequality, which for the case of dynamical systems, for stochastic, more generally even than stochastic differential equations, is due to Baxendale, actually. A really beautiful paper by Baxendale in '89, which says that it's a little hard to understand. It compares the relative entropy between the push forward of these fiber measures by the cocycle and the base point of the cocycle. Sorry, the base point of the evolution. It's hard to understand, and so omega is here. So you first look at the relative entropy for each omega, and then you take the expected value over all the omegas. So, and then this quantity lower bounds the gap between the dimension of the cocycle times lambda 1 minus the sum of the Lyapunov exponents. And if you're under some conditions, you can actually prove that's an identity. That's an equality. This is a really deep inequality, and it's sort of too hard for me to explain on a slide, but also not kind of ludicrously hard. So it's sort of some tricky uses of the ergodic theorem and formulas of this type. So being able to understand how Lebesgue measure is deformed by the flow maps of your underlying dynamical system and your cocycles. But yeah, it's not obvious why you get relative entropies, I would say at first. That's a little bit not obvious, I would say. And the basic takeaway, I don't want to get too far into this aspect of random dynamics. If I have time, I'll maybe discuss that more at the end on the third day, but not going to talk about too much more today. The basic idea is that this essentially says that, so if your system is volume preserving, so this is here, then if lambda 1 is 0, then this has to hold almost surely. So this particular type of degeneracy has to hold almost surely. And there was actually some work in the infinite dimensional case, which gives you some kind of measure theoretic version of this identity, even though this doesn't make sense in the infinite dimensional case per se. So the work we're doing is kind of a cross between Baxendale and Drapier in some sense. Right. So what does this actually mean for us? So it's the thing is, if you look at it, it's clear there's an almost sure degeneracy from this statement, right? Because there's an omega here, and there is sort of an omega here wrapped into ZT. So omega is in ZT. But you see, if there's more than one way to go from Z to ZT, there's more than one path. If more than one omega goes from Z to ZT, then you have something very interesting, right? Because this is the same. This only depends on where you ended up, whereas this depends on the entire trajectory. And so this is a really strong, almost sure degeneracy. But it's sort of like a conditioned on endpoint degeneracy. That's crucial. So the proof of this theorem is right. So now, how do you get from this degeneracy of this weird measure theoretic degeneracy to this intuitive thing in this intuitive thing? This is basically goes back to Furstenberg, which is this beautiful lemma about if you just think about one matrix preserving a measure on projective space, or sorry, you think about the subgroup of matrices preserving a specific measure on projective space, then you get this dichotomy. So the whole dichotomy comes down to this lemma. So you think of one projective space measure, forget about nu z, nu zt, or whatever. You look at all the matrices that preserve this measure under the push forward, and this is a subgroup. And there's two options. Either the subgroup is compact or it's not compact. And if it's compact, then you can prove that there's an inner product such that they're all acting as an isometry with respect to this inner product. This is actually the easy case because you can use the harm. It's defined in terms of the harm measure. You're integrating over the harm measure on this subgroup because it's a compact subgroup of SLD. The non-compact case is much harder. So if your subgroup is non-compact, that's where you get the lines. This is a little hard to explain why this is why it works like that. So basically, if you're non-compact, you get matrices that are growing, and if you're growing, you need to be sort of concentrating on sets because of this lemma. And if you're concentrating on sets, you're going to be preserving kind of lower dimensional sets in projective space, so lines and planes and stuff like that. Yeah, if you play around with that a little bit, you get this beautiful lemma, which in the form of stating is actually due to Furstenberg. But this lemma is for basically what happens when zt is equal to z. So you're looking at trajectories that start at z and map back to zt, or sorry, map back to z. And all right, that sounds a pretty probability zero event. So it's really hard to, or it's not so obvious to prove that somehow this set is relevant and that you can use this lemma. It's really hard, or at least not super obvious. How do you extend, once you have this for one point z, you need to show that that somehow it's relevant for all z's, or that all the z's get sort of a coherent set. And you need to go from kind of sort of a mu almost every statement to a pointwise and define everywhere in phase space with continuously varying things. And so that's where things get hard, and it is hard, and I'm not going to talk about it. So, but you know, it's especially hard in the infinite dimensional case, but even in the finite dimensional case, it's not that obvious how to do it. That's where sort of this strong Feller thing is really crucial. But suppose you have this lemma. Suppose I just tell you that this lemma is true. What do you have to do? You have to prove. So let me kind of erase some of this junk. So what do you have to do? You have to prove that neither of these two things can happen. So if you rule out A and you rule out B, you're done. And so basically what you want to be able to prove is that if we start at 0x, so zero velocity field, and there's nothing special about zero other than the fact that it's easy to work with, and we start at some position, the particle is at some position on torus. We want to know that if we go to another place or back to the same place, it doesn't matter. The lemma is general enough. And at time one, that we can at the same time rotate v in any direction and stretch the flow map and an arbitrary amount. So we want to know basically that we can stretch the flow map in any direction in a unit time step with positive probability. So why would that prove it? So that says basically that there can't be an isometry because I can create an arbitrarily large, I can create arbitrary large deformations of the flow map. So there can't be, the gradient of the flow map can't be acting as an isometry, because then it would be bounded, so almost surely. It can't be preserved. And if I can prove that I can move the projective process anywhere I want, so basically if I can prove that this growth occurs in any direction I want, then it can't be preserving some set of lines because I can move this line, I can map any particular line to any other particular line. So that rules out this and this. And so we sort of reduced it to now basically proving that you have a positive probability of sort of stretching in enough directions so that you can connect 0x to 0x prime or even 0x back to itself. But we do need to prove that you can connect 0x to 0x prime for other reasons. While also stretching in any direction. And so the idea is a classical one now, which is you need to, if you want to prove that you have a positive probability of doing something, a classical technique is to construct a control. So construct an like if you just say, oh, what if the noise path did exactly this, then it would work. And then you say, all right, but the random noise path actually has a positive probability of doing whatever it is that you want, essentially. Maybe with a ridiculously small probability, but a non-zero probability. Again, approximately. And that's where you really need continuous variation of these things. And so, if you can construct a deterministic control, so you change the problem to this deterministic control problem, then you use some stability arguments using regularity of the velocity field and well-posedness and parabolic regularity and blah, blah, blah. That basically you can prove that if the deterministic control can do it, then the random control can kind of approximately do it with positive probability. And doing the deterministic control is now becomes like kind of a fun sort of game. So for example, if you wanted to move, one particle to some other position, what you could do, so the one nice thing is that because we're on a torus, shear flows, so eigenmodes of the Laplacian are both exact, so they zero out the nonlinearity and they're eigenmodes of the Laplacian. So if you force exactly on eigenmodes of the Laplacian, you don't need to worry about the nonlinearity because they're stationary solutions for Euler. And your solution will evolve exactly as a eigenmode of the Laplacian. And so you can solve this control problem by just using basically translations of these three flows. So you don't need to use high frequency anything or whatever. That's completely irrelevant at this step. Like if you wanted to move this particle here, you just drive it, you take the control and drive it to be this shear flow, and then the particle moves here. And then if you want to move it here, you stop the flow, then you drive it to be this shear flow, and you move the particle down here. And then if you want to move V, so V is here, you can move it anywhere you want by putting it, you can rotate it in any direction by putting it in the center of this cellular flow. And if you want to stretch without moving it, you put it at the hyperbolic point, for example, or that'll work. And then the Lagrangian flow map will stretch exponentially and x won't move at all. And so you see that you can move the particle to where you want, then you can stop, and then you can turn on these cellular flows to rotate V and then stop, and then turn on this cellular flow shifted to stretch V, to stretch the flow map in however much you want. And then you just say, all right, well, I have a deterministic control that can do it. And so I have a positive probability of doing it. And so, boom, Lagrangian chaos. And so the key point that sort of made this engine work is that you had to do a bunch of work to prove that because I'm dealing with a random dynamical system, all I really have to do is rule out that something insane doesn't happen. And this is always the intuition, right? So you sort of get chaos in volume preserving system. You're going to get chaos unless something kind of abnormal is happening. That's the intuition, right? And so that can actually be done for this kind of random dynamical system. And it's very important that it's incompressible. So that's Lagrangian chaos, or a sketch of Lagrangian chaos. It's not enough to prove what we want to prove, but I don't want to get into it today, but maybe let me just mention that one of the things that we are working on is proving, so these slides are what I'm going to be talking about on Thursday. But one of the things that I want to mention, because I'm just talking about Alla Furstenberg right now, I have like a few minutes, which is Alla Furstenberg is really rigid and not quantitative at all. So by really rigid, I mean that if you have even a little bit of compressibility, it just flat out does not work. So if your flow is not incompressible, this does not work at all. And everything is false. So the dichotomy is completely false. It doesn't work. Everything doesn't work. And also it doesn't give you any quantitative information. So if you have like a small noise limit, this doesn't tell you what it, how it depends on the noise, as a function of the noise. And so one of the things that we are working on right now is basically to develop kind of more quantitative tools in random dynamics. And actually, to be honest, the main motivation is to study Eulerian chaos. So be able to prove that the Navier-Stokes equations are chaotic in their actual phase space, if you pick the viscosity small enough. We've not succeeded in doing that yet, not even in finite dimensions, where it's also open. But we have succeeded in doing that for some classical systems. So for example, this particular nonlinear ODE called Lorentz 96, which is classically used to benchmark numerical simulations, for example. And the point is that here you have, so forget about the details. It's just it's a chain of oscillators, think like 100 oscillators or something, that are coupled in a nonlinear manner. And there's some damping. And let's say we're going to drive it with some small noise. And the thing is, a la first invert theory does not apply. So because of this damping. And so that doesn't work. So we have no, so that doesn't tell you that it's chaotic. And then the dynamics in phase space are super complicated and will never be understood completely by humans. And so you can't just solve it and just be like, oh, that's the answer. Nope. And so there was basically no mathematical technique that could really prove that the system is chaotic, even though it's random. It's still a stochastic differential equation. And so that's what we worked on. So we succeeded there. And we get some quantitative information, but really, really weak quantitative information. The proof is based on basically finding a new version of that relative entropy formula. So we found a time infinitesimal version of the relative entropy formula. And so it's a long story. I'm not going to get into the proof, but just to say, what is it that we are doing right now is to fix this glaring, I would say glaring problem with our first invert theory. So we got kind of lucky in Lagrangian chaos. And that's, again, one of the reasons why the bachelor regime is the simplest regime to study, because you don't need that much quantitative information as a function of nu or anything like that in order to get to the physical answers. Okay, that's all I'm going to talk about today. So I think I will leave exponential mixing for Thursday, which will certainly not fit in 1 hour, but that's fine.
Well, thank you very much, Jacob.
Hmm?
Thank you very much.
Yeah, very
Other
welcome.
questions? Do we have questions? I didn't check the chat recently. I guess you finished early enough, but if you want to give us a small preview, I guess, of next lecture, or say something else, if no question comes in.
There are a couple of questions, in fact.
I think, new ones, sorry, I didn't.
Chat? I don't see the chat.
You'll see.
So one of them, I think, I already asked before.
Oh, yeah, that's right. Yeah, that was
That's the same one. Oh, yeah.
Is there a
I would say,
connection? Sorry.
What's the question
Yes?
coming?
There's some talking about stretching and compressing with some of the matrices. Is there a connection with vortex stretching?
Yeah, definitely.
Those kinds of matrices?
Yeah, definitely. I mean, vortex stretching. So if you think about so you think about the vortex equation that's like this, the vorticity transport. And let's just think about without viscosity, because who cares about viscosity for a second? Then the vorticity will be something like this gradient of the flow map. Maybe transpose or something applied to the initial vorticity composed with the phi t inverse, right? This is the frozen in law.
Right.
And so exponential stretching of the flow map kind of you believe in your heart should mean exponentially fast vortex stretching. And so and it really seems like it should do that, right? Okay, but that does not quite follow essentially specifically because of the lack of quantitative information as a function of nu. So if we think about, we go back to our setting, so our setting is like this. And so let's say we don't care about scalars, and all we care about is proving, everything we can about Navier-Stokes. The thing is, we say, okay, well, the Lagrangian flow mass is chaotic, so that should mean exponential stretching of the vorticity. Not really, though. We don't know, right? Because what could happen is that maybe the Lagrangian chaos exponent, maybe the vorticity stretching is so small that it's still overpowered by viscosity for all powers of nu, for all values of nu. We know that's kind of true when nu is very large, right?
Right.
There's no sense in which you have kind of a lot of chaos or exponential stretching of anything. I mean, the Lagrangian flow map still has exponentially stretching, but that has no effect on kind of like the nonlinear dynamics of Navier-Stokes itself. It has effect on the scalar. It doesn't really do anything to Navier-Stokes because this guy dominates the dynamics. And in your heart, you want to believe that when this guy is really small, the nonlinear dynamics are being kind of transport dominated. And so you should see a lot of exponential stretching. But to do that, you need to know that the Lagrangian chaos doesn't go away somehow when u goes to 0, which of course is completely counterintuitive and weird and crazy, but we don't have a proof of that, not even close yet.
Okay.
So that's another example why we really need more quantitative dynamical systems tools. So we really need to be able to estimate Lyapunov exponents. And so that's why that's our main, that's been our main research. So since we proved Bachelor's law, that's been what we've been working on, is trying to develop techniques that can estimate Lyapunov exponents for systems that we don't understand completely. So, for this system, there's never going to be, oh, I solved the Navier-Stokes equations. No, give me a break. That will never happen. And so you need to be able to develop tools that can study systems that you will never understand completely. And so you need very robust techniques. And so developing robust techniques to estimate Lyapunov exponents is what we've been concentrating on in 2020. For this reason, because it looks cool, right? Yeah, maybe we can prove exponential stretching and get to anomalous dissipation for Navier-Stokes, but we're very far away from that right now, unfortunately.
Thank you very much.